We're going to end at 6:30 because the department needs the camera to photograph to videotape the public talk tonight by Matt. I think we should all go to that talk, so when Tom takes the camera, we'll just end the lecture and walk over to Keller Hall, which is somewhere in the Popejoy complex. And then keep in mind that the physics colloquium this week, instead of being on Friday in Dane Smith Hall, is on Thursday in something called the Science and Math, or Math and Engineering, or Engineering and Math Learning Center. It's sort of halfway between Dane Smith and the library. A little closer to the library. It's a little bit north of the library. And
on the thing it says it's back in Dane Smith.
What?
On the podium, it says they like cross out and it says Dane Smith.
Oh, it's now in Dane Smith?
That's what I heard.
And
So
was
they
they
take it,
On the podium, yeah, but that could be.
Who's organizing it? Just them.
Jim Thomas would know. So some of us. I will try to send the class a message saying where the colloquium is. All right. Any questions?
I had a question about the talk still. But the one tonight is going to be. Is that going to be the same talk that he's going to give tomorrow?
No.
But I mean, of course, it's going to be like more detailed.
Tomorrow is going to be much more scientific.
But it's going to be the same idea, right?
Well, it's, both are going to be have to do with astrophysics and astronomy and cosmology and the cosmic microwave background radiation.
Okay.
Incidentally, there's an old but very nice book on the discovery of the CMB by Steven Weinberg called The First 3 Minutes. It's the first few chapters read like a really good novel, and then he remembers that he's Weinberg, and he's still writing to the general public, but he includes appendices which have the equations for most of the comments in the earlier part of the book, and well, anyway, it's I think one of the best examples of science writing. Talking about The First 3 Minutes by Steven Weinberg. It's just an excellent book. Okay, we were talking last time about something that was a little bit abstract and maybe a little bit hard to follow, so I'm going to give you another description of it. And namely, this is that if you have charges coupled to a spin 1 massless particle, then Lorentz invariance gives you charge conservation. And in the general sense, what is happening is that your total amplitude is basically something like minus E times the sum over incoming charged particles of some Fi of 0 Pi dot epsilon over Pi dot Q. Q is the momentum of the photon. And then you have to subtract out a sum on the outgoing particles of Fi of 0. Oh, I left out one of the important things here, namely, this is actually M0, and something that Schwartz doesn't make explicitly clear is that m0 depends upon all the incoming and outgoing momentum. So in other words, we've got some process like this, with a bunch of particles coming in, a bunch of particles going out, and we imagine that there's an extra photon that is, let us say, either absorbed or emitted, and it can attach, the total amplitude then will be this one plus this whole thing, and now it'll be that one, etc. And you'll attach it to each of these lines, and then plus, and so forth. Okay, so it's the sum of all those diagrams. And we're doing this in a limit where Q, the momentum of the photon, goes to 0. Photon being massless, you can take that limit. And this thing here, of course, is m0, and it depends upon all the charge lines, P1, P2, P3, and so forth, in, and then the P's out. And since we're doing this soft limit, Fi is the form factor, and this is again pi dot epsilon over pi dot q. This is what happens to the this is basically the propagator of this comes from this propagator of the charged particle. And remember, in the denominator, you're going to have pi, depending on whether this q is going in or out, it's pi plus or minus q squared minus m squared, well, plus I epsilon. And then up here, for various reasons, you have a pi dot epsilon. In the case of scalar QED, the pi came because there was an explicit derivative. In the case of actual electrodynamics, the gamma matrices conspire to produce an extra momentum in the numerator. And so you get this structure. Now the pi squared cancels the m squared, so this then becomes just pi dot epsilon over plus or minus 2 pi dot q, and the q squared we blow away, and the epsilon, I epsilon we forget. I mean, we could have it there, but, well, it's not a loop anyway, so it doesn't matter. These are external lines, so that we're not integrating. Well, yeah, maybe integrating. That is an internal line. But anyway, we're ignoring the I epsilon. And so we get those factors. And then over here we again have m0 of all the pi's. And since we're in the soft limit, all the pi's are the same here and here, so we can factor this out. This f0 is just, remember, by dimensional analysis, this form factor was pi dot q over m squared, but in the soft limit, that's just f of 0. And so you can factor that to minus e m0 of all the pi's, and then what you have is a sum on in of fi of 0 minus the sum out fi of 0. And, well, I forgot to say something critically important. What happens is that under a Lorentz transformation, the massless photon field suffers a gauge transformation, and so the epsilon changes by a q, and the change then in the amplitude due to the gauge transformation associated with the Lorentz transformation is to change this thing by something that has a q here. And so then the pi dot q cancel in the numerator, cancels the pi dot q in the denominator. And so what this thing here is not total m, but it's the change in m is equal to that. And now we want that to be 0, and so for that to be 0, we have the sum of incoming fi of 0 minus some outgoing fi of 0. These are form factors at zero argument, but we can think of them as their effect. To lowest order in a simple theory, this would just be the charge of the incoming particle and the charge of the outgoing particle. So, and in a more general context, we can think of this as more a generalization of charge. So this gives you charge conservation. And this is one of Weinberg. Weinberg wrote a series of quite remarkable papers in the mid-60s. My memory of it is, and I was not hanging around with him at the time, but my memory of it is that, well, the rumor is that he was originally at Columbia, but he and T.D. Lee didn't get along. And T.D. Lee, of course, was a Nobel laureate and senior professor. And so Weinberg had to find another job, and he went to Berkeley. And then at Berkeley, he wrote a series of remarkable papers which inspired much of Schwartz's book, and which then Weinberg expanded or contracted into his 3-volume set on quantum field theory. Let's see, I was going somewhere with that, but now I'm a little bit and this idea that charge conservation follows from Lorentz invariance from massless spin 1 fields is something he explained in one of these papers. They're all phys rev mid-60s, maybe late 60s. Okay. Now, if we're talking about a spin 2 massless field, which Weinberg was also considering, then what happens is under a, here the analogous, the analog of a gauge transformation is a general coordinate transformation, or a, which is related to a Lorentz transformation. They kind of occur together in GR, and so this is then epsilon mu nu plus alpha mu q nu plus alpha nu q mu plus something else beta q mu q nu. Schwartz uses capital lambda, but the trouble is that suggests that it's part of a Lorentz transformation. The vertex here that we're thinking about is pi in pi plus q out, and this is a graviton momentum q, and so what we would say is that this particular vertex, or that Feynman diagram, is gamma mu nu of p and q, and the essential part of it is minus 2i p mu p nu some f tilde of p dot q over m squared. So that's the pq k for this case. And we're perhaps already, if we're going to the short, we're going to be going to the soft limit where q is essentially 0. So we're really just going to have f tilde of 0. And so now what you're supposed to think about is that we've got some complicated process here with a lot of particles coming in, and What we can do is this particular particle, well, we can say we change it like that. So there's a P1 plus Q1, or actually this P1 plus Q1 is going this way. Anyway, right, so there's a graviton going off with Q. Anyway, we imagine attaching an extra graviton to many of these lines coming in and summing them up. So in other words, all right, let's do the simplest case. Suppose it's 2 by 2. Let me start over. So suppose we're talking 2 by 2. Okay. So what we'll do is we'll use this vertex and we'll add one graviton to this one, plus that one, plus that one, plus. Okay, so it looks like this, and that's the amplitude, say, for a 5-particle process in which, for example, there's an extra graviton coming in or going out, and it can interact with all of these external legs. You say, well, what about interacting here? It can also interact with one of those lines there, but then it's not important because you don't have this effect of, it's only an external line that has p squared canceling the m squared. If it interacts with a loop line, then you don't get p dot q in the denominator. You get something much more complicated you're integrating over. And this thing doesn't get, see, p dot q gets really small when in the soft limit of q going to 0, so this term gets huge. Becomes huge. So we ignore all of the external gravitons interacting with internal lines here. We just consider the external lines. And this big amplitude then, which is the sum of all these things, we can factor out this in the soft limit. These are the external lines. Okay. 1, 2, 3, 4 in this particular case, but in general, n external lines. And then adding up all these terms, we're going to get a sum on in f tilde, that's this thing, soft limit, so it's 0. And then if we imagine what we've got is p mu epsilon mu nu p nu over pi dot q, and then minus a sum out of the same thing, f tilde is 0, p mu I epsilon mu nu p I nu over pi dot q. All right, so this is the thing that we start with, and now we say, well, under a Lorentz transformation, this spin 2 field is going to have a polarization vector that changes by, in other words, what I should have said here, this is q. And the epsilon of q changes by that much. And so what is the change? Let's look at a particular one due to a particular change here. And so we have the change in pi mu, epsilon mu nu, pi nu, over pi dot q. What's the change in this? Well, I'm just going to change this guy. I'm going to have the change in, I'm just going to put the change in there, so just these 3 terms. So this is equal to pi nu over pi dot q, and now the change there is alpha mu q nu plus alpha nu q mu plus beta q mu q nu. All right? All right. Now, Well, what is this? This is just P dot Q, which cancels the P dot Q. This one on that one is P dot Q, which cancels the P dot Q. And this one in the soft limit we blow away because it's order Q squared, 0 squared. Okay, so what we wind up with here is, but in any event, the Q contracts, let us say, with that one and still cancels. So what we get here is 2 alpha mu pi mu plus beta P dot Q. So that's the change. And we're going to forget this one in the soft limit. Okay, now, so what we want is that the change in the amplitude due to the shift in the polarization due to the Lorentz transformation and the masslessness of the graviton and so forth. Waving the hands a little bit there. 0 is delta m, and what will this be? Well, this thing here is just the original amplitude before we've added any gravitons. Thought graviton, there's only one added graviton. So we can factor that out, and that's m of all these external momenta. And then there's an alpha mu and a 2. And what do we have? Well, we have something or other, which I'm going to call kappa I, pi mu, on the incoming, and then the outgoing kappa I, pi mu, where, what is kappa I? Kappa I is essentially alpha. Or is it alpha pi mu? I know, I don't know. No, pi mu is still there. Oh yes, kappa I is the Fi 0. And the Fi 0 is basically what this thing is. Okay, the coupling. All right, now, this is really quite cute. Oh yes, I skipped that line. Kappa I is F tilde I of 0. 0 meaning soft limit. So if we're going to have Lorentz invariance, what we have is 0 is, or equivalently, sum in kappa I pi mu equals sum out of kappa I pi mu. Well, we already know from Lorentz from Poincaré invariance, translation invariance, that the sum in of pi mu is equal to the sum out of pi mu. That's just formal mental conservation. For sure, that's true. Okay. And now, what Schwartz points out, translating Weinberg, is that these kappas had better be all the same. Otherwise, we've got a problem. And that's sort of intuitively clear, but it becomes crystal clear if we actually take an example of, say, 2 by 2, 2 to 2 scattering. 2 particles to 2 particles. So then the Lorentz, the Lorentz conservation of formal momentum gives us P1 plus P2 is P3 plus P4, not P3. All right. Suppose these kappas, just to take an outrageous example, suppose instead of being 1, 1, 1, 1, we're 2, 1, 1, 1. All right. So then this equation would give us 2P1 plus P2 equals P3 plus P4. Well, this would give us the crazy equation 2P1 equals P1, or P1 equals 0. Well, we can't have that. So that's an example of what would happen if the kappas aren't all the same. And so what does this mean? This means that gravity couples universally. That that this thing here doesn't discriminate. It just couples to P mu, P nu, which is effectively coupling to energy. All right, so that's basically Schwartz's distillation of some of these very, very imaginative papers by Weinberg. I remember when I first saw these papers, this was back in, I regret to say, mid-70s. I was so grateful to see them because I never really understood what was going on with how fields transformed onto Lorentz translation. I mean, I knew roughly, but Weinberg makes it actually precise and clear. And all right, now chapter 10 is about group theory and spinors. What I propose to do is the following. You guys read chapter 10 in Schwartz, and I also put my treatment of the Lorentz group and spinors on the class webpage as a PDF. And I'm going to give you my treatment, then you'll see two treatments that are slightly different. Both treatments, by the way, are completely influenced by Weinberg. So it had been, if Weinberg hadn't written those papers in the mid-60s, probably neither Schwartz nor I would know what the hell's going on. All right. Okay, so let me review what the inner product is. And since I'm following my notes here, I'm going to be using the other metric, but you know, it's just say, well, he's old and can't switch. So what we have is that xy is invariant, and this, of course, is, in this metric, it's x dot y minus x0, y0, and the idea is that this is the same thing as x prime, y prime. And we can think of this as x transpose eta y, where eta is this metric of a flat space-time, which is just -1, 1, 1, 1, or in Schwartz's language, 1, -1, -1, -1. And I think this is the better metric. The only advantage of the Schwartz metric is that you have p squared is m squared, which kind of makes us feel warm inside. But whereas with Weinberg, p squared is always minus m squared, and whenever I see that, I always, but anyway. All right, so there are these two ways. So what we're saying, this is sort of review, but there's no problem reviewing things a little bit. This is x prime, y prime, and we want that to be, that of course is x transpose L transpose eta L y, and we want that to be xy, which is x transpose eta y. And, well, this thing will always be true as long as L transpose eta L is equal to eta. So this defines a 4x4 Lorentz transformation. We've been through this before. If you take the determinant of this, you see that the determinant of L squared is equal to 1. So the determinant of a Lorentz transformation is plus or minus 1. Now the Lorentz transformations that we want have determinant 1. Those are the proper Lorentz transformations, and we're also going to be focusing on the orthogonous ones, which is Greek for keeping time straight. Any questions? Okay. By the way, the fact that this is works this way, you see you can multiply from the right by eta, and you get the equation L transpose eta L eta is equal to eta squared, which is the identity. And then that tells you that, I'm sorry, I wanted to multiply by the left, from the left, there. And that then tells you that this, of course, is L inverse L, and so L inverse is eta L transpose eta. So there's something very simple about Lorentz matrices, although any 4x4 matrix that isn't the identity is too much for me to deal with. But in fact, the inverse is very simple. It's just eta L transpose eta. And if we're talking this way, like, let's use Latin. If we're talking LAB, then L transpose AB is L, whoops, let me write it where I have space. It's LEA. So you just shift things like that. And the first index is the row index, the second index is the column index, and whether it's up or down depends upon whether you screw around with an eta and so forth. All right. Okay, so as usual with group theory, at least continuous group theory, the whole story is contained in the part of the group that's really close to the identity. And so these things are then 1 plus omega, and in other words, we're saying L is I, the 4x4 identity, plus some 4x4 matrix omega that's small. All the elements of omega are small. And so the equation then L transpose eta L equals eta, well, this is just I plus omega transpose eta I plus omega equals eta, and that tells us simply that omega transpose eta is minus eta omega, or that omega transpose is minus eta omega eta. So in other words, this omega has to be a 4x4 matrix such that when you hit it from the left and the right with eta and have a minus sign, you just get a transpose. Okay. And what you can figure out is that there are basically 6 independent omegas. And I can write them down. I can write them down as R1. And so this is a 4x4 matrix like that. R2 is a 4x4 matrix, but we have a 0, minus 1, 0, 0, 0, 1, 0. So it looks like that. And then R3 is looks like, well, 0, 1, minus 1, 0, and everything else is 0. And the other 3 matrices, these are the rotation, these generate rotations. These are the ones that generate boosts. And this is 0, 1, 1, 0. B2 is 0, 0, 1, 0, 1. Notice these are symmetric, these are anti-symmetric. Okay, so these are the 6 generators of Lorentz transformations. The top 3 generate rotations, bottom 3 generate boosts. And I must say, I don't quite know why I chose to label them as 1, 2, 3 right now. Well, actually, 3 makes sense because this is a rotation about the z-axis, so this screws around with 1 and 2. Oh, it actually, everything makes sense. Okay, I didn't screw up. R1 is a rotation about the 1 axis, so this screws around with 2 and 3. 0 is up here, that's the time. And the boosts always involve time and one of the space variables. So this is time, and the one axis time, and the two axis time, and the three axis. Okay, so what is a general Lorentz transformation here? Infinitesimal. It's I minus I theta. Well, what I've done, of course, is succumb to the physicist's fetish of making things Hermitian. You see, we want to make this guy Hermitian. Well, it's anti-symmetric and real, so it's anti-Hermitian. We multiply it by an I, it becomes Hermitian. So we multiply all these guys by an I, and they become Hermitian. But we multiply also these guys by our I fetish, and they become anti-Hermitian. And so what we have then is minus I theta L, IRL, so that this thing is Hermitian, and minus I lambda j I bj, and these guys then are anti-Hermitian. And we're going to rename these. We're going to call them I minus I theta L JL, so this generates rotations, is the angular momentum generator, minus I lambda j kj. Those are the boosts. And so you see, this thing is not unitary. This much of it is unitary, at least in the infinitesimal theta limit, or if you exponentiate, whereas this guy is not unitary. Okay. All right. And so what we've got here, in another way of saying it, is we can think of this as I minus I theta dot j minus I lambda dot k. Okay. Now, these are the generators. You can, with your fingers and a pencil, you can write down all the commutation relations. And here's what you find. What you find is that ji, jj is I epsilon ijk jk. Well, that's what you learned in quantum mechanics for angular momentum. Then you learn that ji kj is I epsilon ijk kk. All right, what is this telling you? This tells you that under a rotation, the k's transform as a 3-vector. And after all, these k's generate boosts in 3 different spatial directions, so it's natural that they should transform as a vector. The next one is ki kj, and this is minus I epsilon ijk jk. All right. I have no intuition on this one. I can tell you what it says. It says if you have 2 infinitesimal boosts, and then you reverse the 2 infinitesimal boosts, the net effect is a rotation. And I don't know. Anyway, notice that these commutation relations don't change if you go from jk to j minus k. So we have jk. So whenever we have 6 matrices like that that work, we also have another 6 that also work. All right, now what does this 4x4 Lorentz transformation look like? Its L, of course, is I plus omega, which is I plus theta dot j plus lambda dot b.
Yeah, it's okay.
Yeah, I guess that is okay, because you see what we've done. I just removed the physics fetish and canceled the i's. And what does this look like? well, it's 1, lambda 1, lambda 2, lambda 3, lambda 1, lambda 2, lambda 3, and then 1, 1, 1, and then minus theta 3, theta 2, theta 3, minus theta 2, minus theta 1. All right, so that's an infinitesimal Lorentz transformation. This is all, of course, in the notes. And, okay, so what does this do to some 4 vector? Well, it does obviously, I could, in the book I actually write down what happens to each of these, but there's a cute way of doing it, namely t prime is t plus lambda dot x, where these are the 3 lambdas, and x prime is x. Of course, we're talking infinitesimal here. X plus t lambda plus theta cross x. Cross being, you know, the cross product. Caret being the cross product. So you see this is the rotation. This is clearly a boost. It just shoves the, it shoves x by t. So this is basically vt, isn't it? For infinitesimal, the infinitesimal case. In fact, the infinitesimal case is just a Galilean transformation, apart from the fact that we screw around with time. All right, now, these J and K are really the whole story, but there's a special way of thinking about these generators that is vastly simpler. And this vastly simpler way of doing it is to write J sub L plus minus, and we set that equal to 1/2 JL plus or minus I KL. Okay. Now these guys are Hermitian because that was Hermitian, this is anti-Hermitian, now it's Hermitian. And here's the really, really remarkable thing. And this is a mathematical miracle. Okay, I don't believe in any of the miracles in the Bible, but I believe in this mathematical miracle. And it is Ji plus Jj plus is I epsilon ijk jk plus Ji minus Jj minus is I epsilon ijk jk minus. So the J pluses are an angular momentum, the J minuses are an angular momentum, at least algebraically. And then the marvelous thing is Ji plus Jj minus 0. So that is really wonderful because it means we've got something that's very, very simple. We can think of the generators of the Lorentz group as 2 sets of angular momenta, and we know how to represent groups. We know how to represent the rotation group, namely that we can represent these J pluses as matrices that are, we set little j equal to 0, 1/2, 1, 3/2, whatever. And maybe I should call that J plus. What do I call that? I guess I call it J and J prime. So we pick J and J prime to be one of these half integers. And then we construct matrices that are 2j plus 1 square and 2j prime plus 1 square. We use these guys to represent the j minuses, these guys to represent the j pluses. And these are just the things you learned in quantum mechanics. Of course, we feel confident about the case 0, j equal to 0, j equal to half, which are the Pauli matrices, j equal to 1, but beyond that it gets a little more complicated. All right. Any questions? We've got 15 minutes before Tom Hess comes and takes away the camera because of the... Yes?
So J and J prime are the eigenvalues of these operators?
Well, yes, they're eigenvalues in the following sense. J plus vector squared has eigenvalues on some state, has eigenvalues j plus 1, and j minus squared has eigenvalues j prime plus 1. I'll give you a candy as soon as I get to the front. Okay, so what we're dealing with then for these rotations is a d of j and j prime of theta and lambda, and that would be e to the minus I theta L J L minus I lambda L K L. Okay, that's starting with the original J and K. But you see the J plus and minus are related this way, and you can rewrite the JL in terms of the J plus and J minus. In particular, if you add J plus plus J minus, you could get JL. So JL is JL plus JL minus. Right? Right. And KL is JL plus minus JL minus divided by I. Yes. Okay, so these are the, you see, you can go back and forth. So originally we would have had this, or equivalently, I should have written it backwards. Now that we know what these J plus and J minuses are, we can write this as E minus I theta L minus lambda L JL plus, and then as a separate exponential, because the J pluses and J minuses commute, we have minus I theta L plus lambda L JL minus. So we can write it this way where we know what the matrices are, or that way, where we, now I'm just wondering, actually, if I write J plus, I mean, these two guys certainly commute. Yeah, we can write this as one exponential, because J plus and J minus commute. Once we've written it as one exponential, then we rewrite it this way. So that's, these then are the general representations of the Lorentz group. We've got the whole thing done. Okay, now, of course, there are many implications. So let me first have to replenish TA's candy store. Okay, so let's see. Oh, I am getting low. All right, I'll owe you one, but you get this one. So the rule is, you know, if you correct something, you get two. If you ask a question, you get one. All right, any questions? Good, I'm low on candy. All right, let's see if I can. erase the board then. Okay. All right, now the question is how do fields transform under Lorentz transformations? And this is one of the things that I said, until Weinberg wrote his papers, I don't know, I suppose Sidney Coleman understood how they transformed, and surely Wigner did, but this was not common knowledge. So here's how they transform. U of L, this is an infinite dimensional unitary representation of the Lorentz group. And now we have some psi jj prime, because it has, these are the j's, these are the parameters that tell us what the representation is. And M goes from minus j to plus j in steps of 1. M prime goes from minus j prime to plus j prime in steps of 1. X is the space-time value. U inverse of L. What is this? Well, it's dj0 M double prime of L inverse, and then d0j prime, M prime, M triple prime of L inverse times psi of jj prime, of course, but now M double prime, M triple prime of Lx. So that's the that's how the fields transform, and we're going to specialize, of course, to the simplest case. I mean, well, the very simplest case is j and j prime equal to 0. In that case, M and M prime are both 0. This thing is 1 times 1, and it's just L of x. So that's a scalar field. The next one is the spin 1/2 field. And in the simplest case, you have j equal to 1/2, j prime equal to 0. That's a left-handed spinner. Or you can have j equal to 0 and j prime equal to 1/2. That's a right-handed spinner. You put, and each of them is a 2 spinner, because if j is 1/2, that's a 2-dimensional representation. So now we have 2 different, for the simplest non-trivial, apart from a scalar, the 2 simplest cases are 2-dimensional representations. One is said to be left-handed, and I'll show you why. Another one is said to be right-handed. You put the 2 together, you get a Dirac spinner, which is has left and right together, 4 spinner normally. Okay. All right, I think we can skip all that, and now just jump down to a left-handed case. This is d1/2 0. And so if we look at our equations there for what do we have? Well, we would have J plus would be sigma over 2. These are the Pauli matrices divided by 2. J minus is just 0. And consequently, the J is a half sigma, so this generates rotations. And K is minus I 1/2 sigma. And so this follows from, if you want, well, I can just write it down again, it's easier. This is J plus J minus, and this is K plus minus K minus, no, J plus minus J minus over I. And so this is sigma over 2I, which is minus I ½ sigma. Okay, so this is the simplest non-trivial case, or one of the two simple ones. And the matrix then that represents the Lorentz transformation e to the minus I theta dot j minus I lambda dot k is d 1/2 0 of theta and lambda, these being vectors, 3 vectors, and it is e to the minus I theta dot sigma over 2, that's the theta dot j, and then it is minus I k, but then or plus I k, and then no, minus I, anyway, let me just write it down. Minus lambda sigma over 2. So it looks like that. Another way of writing it is e to the minus I theta plus lambda sigma over 2. And another way of writing it where you don't want to distinguish what's theta, what's lambda, you just say e to the minus z dot sigma over 2, where z is some triplet of complex numbers. And that tells us then that this thing is actually the group SL2C, which means L is linear, S determinant 1, 2 means 2 by 2, C means complex entries. And this thing is then this SL2C, it's the covering group of the Lorentz group, just as SU2 is the covering group of the rotation group. And the covering group is a group that has the same Lie algebra, but is simply connected. And all right, I don't think we need to fool around with simply connected at this stage. Well, simply connected is simple. It means if you have any loop in the space, you can shrink it and stay in the space. Okay, so that's the standard left-handed boost, and we can say a couple of things about it, namely, this boost takes us to momentum p. Well, remember I said one way of thinking about it is we can say a boost in the z direction that takes the vector 0m to p, but in the z direction, or inverse of p hat. Now this has no effect on 0m. Remember, 0m is the, well, actually, if I'm writing things using the same notation as today, then this thing is m0. Okay, because I put the time component up top. So the R inverse has no effect on this. It just rotates 0 into 0. B boosts this thing into P0P, z direction, and then R rotates this thing so that it is P0P. Okay, this is the standard boost. This is the thing that I was referring to when I talked about standard Lorentz transformation that takes you from the fiducial vector to P. And remember, the little group is the thing that leaves this invariant. Well, that's just the rotations of a massive particle. And it turns out you can take the mass equals 0 limit for everything, well, for spin 1/2, no trouble, none of the issues that arise for spin 1 or spin 2. Now, for this standard boost, what does it look like? Well, it's d1/2 0, and first of all, this part here, well, actually, the whole thing is simply 0, there's no rotation, alpha p hat, and it's e to the minus alpha p hat dot sigma over 2, and this turns out to be I cosh of alpha over 2 minus p hat dot sigma sinh of alpha over 2. The witching hour has arrived. All right, so we'll make this 15 minutes up in some later classes, or we'll cancel some time that I already went over previously. And okay.